Hey everyone, welcome back to the start of week 4. We're going to talk about correlation this week. And this is a anxiety provoking topic for me, not because I don't like correlation. I love correlation, but because I usually use the whiteboard a ton when I talk about this material. And I've been struggling to come up with a substitute. I have a little tablet input device now that's supposed to do the job, and I have a little Google Keep sheet that I should be able to write on here. We're just going to give it a go, and if it's a disaster, you won't see this. If it's anything less than a disaster, you're stuck with what you got. Here we go. Uh, just to start things off here, let me get my mouse to work here. Maybe there we go. Okay, yeah. Boy, my mouse, there we go. So this first link here under week 4, if you have not yet watched this video, please stop and go and watch this video. It's excellent. It does a great job of explaining why correlation doesn't mean causation in a lot of cases, and yet why we're curious about thinking about cause and effect with respect to correlation. So if you haven't watched it yet, pause, stop, go back, watch the Ionicus Meets TED Talk that I've got linked right here that says start with this. Then, of course, read Whelan Chapter 4. That's assigned. And then we have a really short presentation here, deceptively short presentation, which we'll get into really quick. Let me get the presenter view going here. This is all going painfully slowly. Let's see if I can click on that and then win. Why does it say win when I click on that? No, that's not what I want. Okay, time to get the other mouse going here. Come on, other mouse. There we go. Okay, I've got 2 different input devices, so hopefully this will work out okay. All right. Whelan brings up this topic in the context of how does Netflix know what movies I like? And to be honest, he doesn't really answer that question as fully as he might. He intimates that it has to do with correlation, but it's actually quite complicated how Netflix knows what movies you like. And Netflix had a contest for a while to see what programming teams could come up with a better algorithm for recommending films to its audience, because this is something that tech firms are really interested in. Is if you like a particular film, then they want to know what to recommend to you, because they want to keep you hooked, because keeping your eyeballs on their service and not on somebody else's ensures that they'll keep your subscription, or in the case of free content like YouTube, it ensures that your eyes are looking at their ads more often than somebody else's ads. So this question of correlation that Whelan's getting at with respect to Netflix is the idea that people who like a certain group of movies probably like other movies that other people like them have liked. So Netflix has an algorithm that predicts your likelihood of liking one movie based on whether you liked a different movie. It turns out that this is just an aside, but while we're talking about this, if you're curious about this sort of idea, Netflix for a while had you, when you would sign up for Netflix or especially when you create a new account, but every once in a while they'd ask you what kind of movies you were interested in seeing. And this is a great example of when we shouldn't always be very trusting of measurement, because it turns out that asking people what kind of movies they like isn't a very good question to ask compared to what movies people actually watch. So, for example, when Netflix would ask, hey, what kind of movies do you like? People would very often select dramas and documentaries, and then it turns out they would never watch them. And they'd watch things like Tiger King, or the equivalent of it, when I guess Tiger King is officially a documentary, but you know what I mean. So people would oftentimes present themselves as very serious, and foreign films. Everyone, clicked like I like foreign films, yes, because they want to be somebody who likes to watch foreign films and likes to watch documentaries, and then they end up spending their minutes watching, pulpish sort of either staged reality TV kind of things, or maybe action movies or whatever. And I'm not judging, right? This is me too. But it's an interesting thing. And so Netflix wanted to figure out, based on the movies that you watched all the way to the end and said you liked after you watched them, if they could predict what movies you would then like, and so it could recommend reliably to you a film to watch. And that's an interesting sort of problem to have. So that's what Whelan gets this the teaser of this chapter into here. But let's get into where's my mouse? Man, it's going to be one of those days. All right, let's get into this idea about correlation. So with correlation, we talk about the degree to which two phenomena are related to one another. And I'm not going to, boy, my mouse. The struggle is real today. There we go. Okay. I'm going to try see if I can get into it right away here with the pen, see how well this goes. Oh. And so when we talk about a correlation, we're talking about the degree to which two phenomena are related to each other. And so we visualize correlations with an x and a y axis like this. The x is this horizontal axis, the y is this way. But the idea of a correlation is that we'll have two different data points. And Whelan's examples are very concrete, and for that reason I like them, because it's something that we can think about right away. I want to be careful about making too many generalizations about them, and so it's something I always go to great pains to point out in class. But I wonder if I can make this. Oh, I can't. And so we're going to put a little series of dots here on this. And I apologize that I can't make nice round dots every time, because I am still figuring out the technology here, but hopefully you get the idea that these are dots. And you should notice that they are kind of in a line, but not exactly in a line. There are even some outliers. But the idea here, basing this on one of Whelan's examples, is that along this x-axis we're going to put, here is, boy, now this is where the struggle gets. Height is this way. Oh, man. Just, I don't know. I can really do this a lot better on a whiteboard. I'm not kidding. I'm going to try and not get the feedback and see what happens. Whoa, okay. It kind of works. So writing without actually looking at the screen is easier for me, although the scale gets really out of whack, but I just, wrote it down there. And so this is going to have to do. Here we're looking at the relationship between height and weight of individuals. Each dot is a person. So each person has a height, each person has a weight. And what we're observing is that there is a general pattern to the relationship between height and weight. It's not a perfect relationship. It's not that if we know someone's height, we know with 100% accuracy their weight. But we have a range here. We know that if someone is on the shorter end of things in height, that their weight falls within a range, and it's in this range. So either a lowish weight or a mediumish weight. If someone is in the medium end of the scale in height, we see that there's a whole range of weights here. So they're in the not all the way to the lowest, lightest weight, and not all the way to the heaviest weight, but there's a range of weights, and we know that people of medium heights tend to be medium in weight. And then when we see here, the tallest people tend to be the heaviest people. If your brain is instantly saying, well, what about? Yes, there's going to be outliers, and especially in a bigger population, there will be outliers. So there'll be someone who is exceptionally tall and exceptionally skinny, for example, right? And so there'll be an outlier maybe down here, right? There might be somebody who is shorter in height and particularly heavy set, and there'll be an outlier up here, right? But we do tend to observe that because shorter people have less mass overall and taller people have longer bones, that there's a general relationship between height and weight. What we can do is unscientifically just draw a line through those dots and say this is a relationship between height and weight. That's correlation. We're saying if we know somebody's height, we can predict plus or minus some uncertainty, we can predict their weight. Or vice versa, this works both ways. If we know someone's weight, we can predict with some degree of accuracy their most likely height. Do we know every time? No. Do we know to the nearest gram how much somebody weighs? No, not at all, right? But we have a general idea. The reason we're interested in that is because if we know one variable and another variable is difficult to observe, or we want to predict the other variable, then having one that's observed or knowable gives us a lot of power to predict the other so we know more about things. We're interested in regression, I just said regression, but we're interested in correlation for that reason, is we want to be able to tell an unknown variable from a known variable if we can. Or we want to figure out whether one variable might be causing another variable, which we're going to get into as we discuss this whole chapter a little bit more. Not for this lecture, don't worry, but as we get into it a little bit more, we will. The correlation coefficient is unitless. And the reason it's unitless is because it reflects the extent to which two variables co-vary or not, meaning that if the position on that x-axis is highly predictive of the position on the y-axis, then we see a strong correlation. If the position on the x-axis is not predictive of the position on the y-axis, then we see no correlation. So it's unitless. It's either strongly positive, strongly negative, or in the middle, which is no correlation. And the possible range of the correlation coefficient is between -1 and 1. Let's go back to the whiteboard here if we can. And this is working okay for me so far. I don't know. I'm not going to get too cocky here, but and we'll draw another one of these relationships. Now, I can have a strong positive correlation that looks like this, and a +1 correlation goes from the bottom left corner to the top right corner. And the way to think about this is that increasing values of x correspond to increasing values of y. And the correlation coefficient, by the way, which is abbreviated as R is the correlation coefficient, equals 1.00 in this. Hold on just a second. I've got to run and I'll be right back. Okay, I'm back. And we were just looking at the correlation coefficient for a strong positive correlation. Where's my mouse? Where's my mouse? There it is. Okay. And then we can also draw a relationship like this, where increasing values of one variable are associated with these are all circles. I know that some of them look like open circles. Are associated with decreasing values of the other variable. And again, if I know x on this is a straight line I drew, right, of points, all in the same straight line. If increasing values of x are perfectly associated with decreasing values of y, or vice versa, equals -1. So I didn't have to put the 1.00 there, but you get the idea. This is -1, that's +1. That's messy. It's a messy one. Let's see if I can make it better. But wait, there's more. The angle of the line doesn't matter. And this is where this is worth, and I realize I'm taking this slow. Some of you might be yawning already, but it's worth taking our time to think through a few of these things. If I've got a very, oh, I can do that? Oh, I can do that. Whoa, okay. Still learning here, people. I'm still learning. All right. I have a button on my pen that can do things. All right. So let's say I've got a relationship between x and y where it is not as steep of an angle, but it's still a straight line. Sometimes the intuition is to think about like the slope of the line as the correlation coefficient. That's not it. This is still a correlation coefficient of 1 because it's not about whether the line is steep or flat. It's about whether, to the extent to which I can predict the position of y based on x. And similarly, I could have a really steep negative slope. And again, the slope is not what matters. It's the relationship between y and x, and this is still a perfect negative 1. Now, if I start getting fuzzy, meaning, oh, my button's not working now. Can I erase? Oh, I can't. Good. Okay. So I'm sorry if you're just like rolling your eyes out of your head at this old guy trying to figure out technology. Then I understand. I'm not trying to be too dramatic about it here, but I'm just trying to figure this out as I go. So similarly, not similarly. I just did similarly. I just did that. Let's talk about a correlation coefficient, and I'm not going to guess a correlation coefficient because it turns out I'm pretty bad at it, and a lot of us are too. But if I had a relationship that was like this, where there's a more or less linear relationship, but it's fuzzy. I can't perfectly predict where on y I will be based on my x or vice versa. Or similarly, but the opposite direction, if I've got a fuzzy, that line wasn't meant to be there. You get the idea, but that's still. Clean those points up. There we go. And so we've got a little bit of fuzziness here. So again, my position on this axis isn't perfectly predicted of my position on this axis, or vice versa. But I have a general idea. This is a correlation coefficient between 0 and 1. And this is a correlation coefficient between 0 and negative 1. A correlation coefficient of 0 means that there's no relationship, and that would look something like this. This is just one example. You can have other correlation coefficients of 0. But let's take a minute to think about this. And I think that for people who have been feeling like, whoa, you're drawing a lot of stuff and I don't get it, this is a good place to sort of bring this back into what we're talking about. Whatever the value is here, what I'm saying when I look at this, all these points all scattered all over the place here, if I know that this value of x here, if x is low, do I have any idea whether y is high or low? I don't, because there's low values of y associated with low values of x, as well as high values of y associated with low values of x. And then if I get to medium values of x, I see low values of y and high values of y. If I have high values of x, then I see low values of y and high values of y. So what I'm saying when my correlation coefficient equals 0 or close to it is that there's no relationship. No relationship between the variables. That is, I cannot predict where I am on y based, even approximately where I am on y, based on my position on x. Whereas here, I'm saying there's a positive relationship. I'll write that in here if I can. Wait, what happened? There we go. And then this is a negative relationship. So the positive relationship tells me that the higher I go on this axis, the higher my values of x get, so too the higher my values of y get. Here, the higher with the negative relationship, the higher I go on x, the lower I go on y, or the lower I go on x, the higher I go on y. No relationship says it doesn't matter what my x is, I can't predict y at all. So we're interested in positive and negative correlations when we come up with a zero correlation or a very weak correlation, like a 0.1 kind of thing. We basically say, meh, you can't do very much with this. This is not very interesting to us, right? So let's look at the examples that we have here. Ranges from 1 to 1. Unitless, as I already mentioned. So the correlation coefficient is just a degree of association. It doesn't matter whether we're talking about kilometers or miles or pounds or kilograms or SAT scores or ACT scores. It's a unitless measure. We care about the correlation coefficient. We are very interested in it, but we always take great pains to point out that we are measuring correlation as a statistical measure of the relationship between two variables. And it's a statistical relationship. Correlation by itself is just a statistical relationship. It's not a causal relationship. We're going to get into why we're so interested in correlation with respect to causation. Do not worry. But for right now, just the big lesson is that it means a statistical relationship, and by itself, it's just sort of a, that's cool, that's curious, okay, right? Here's a diagram of these different correlations from Wikipedia, and this is a useful illustration except for all of these are zero correlations, and I think this is kind of useless, I'm sorry, because it's, wow, there's some geometric figures you can draw that has zero correlations. I'm just gonna, how do I do that? Let me just, I can't draw on the slide. I can just point on this slide. I have to use keep to draw. Okay. Well, I was going to try and draw some lines through this, but that's okay. These are all zero correlations. The things to really look at here is look at the positive, strong correlations, 1, 1, and 1 here, negative 1, 1, and 1 here. This is technically undefined. If you had a little bit of variation, it'd still be a zero correlation, though. But these examples up here are much better in terms of thinking about how strongly linear data approaches 1 or negative 1, no matter what the angle is on that line, no matter what the slope of that line is. Whereas if you get a little fuzzy here, you get a 0.8, that's still a strong correlation. A 0.4, you start using terms like moderate correlation or maybe even weak correlation. Negative 0.4 looks like this, a negative 0.8 looks like that, and a negative 1 looks like this. This is a good time to go to our bonus pack, Guess the Correlation game, which is right here. Is this going to open in a new window? There it goes. Yes, it will. And this is, I like the sort of Atari sort of setup here. And We'll just put something fun in here, like UW-Tacoma. The first sexy clicker game called Monster Clash. Boy, I would much rather play a Guess the Correlation game than the first sexy clicker game, Monster Clash. Whatever that is. Man. I would like to support the Guess the Correlation game with some clicks on their revenue producing ads, but I'm not going to click on that because that just looks terrible. Where'd my mouse go? There we go. All right. Man, just the struggle is real. Let's see if there's going to... Okay. Yep. So they want to make sure that they know I'm they're tracking me. They're planting cookies, I'm sure. All right. Let's get started. New game, and we're going to guess the correlation. Now I'm awful at this. I got to tell you. So, but you had those clues from the PowerPoint, right? From the slide deck here. So that's not as strong as a 0.8. I'm going to say 0.5. Now, if you're outside the range, you don't keep going. You have a certain number of lives, but the more right you are, the more coins you get, and the more wrong you are, the fewer coins you get. Where'd we go? There we go. So this one seems a little weaker. I'm going to say 0.4. And it was a 0.64. So you see how good I am at this already. Anyway, I would recommend that you play with this a little bit. And one of the things it'll help you do, it helps me every time, is it helps you not be overconfident about how much you know, because like I was like, well, it doesn't look as strong, and it was stronger. This looks like a weak correlation. I'm going to say 0.35 just for fun. And it was a 0.40. Okay. Let's see if I can hit enter. Yep. And then that's going to be a 0.3. And it was a 0.26. This is like a 0.8. 0.71. This is like a 0.8 as well. 0.77. Wow. So I'm getting really lucky. I'm usually worse at this. I'm going to say 0.5 for this one. Oops. Well, we'll just leave it at that. Oh, 0.62. Okay. And then this is a 0.3. I'm going to say 0.38. And this is like almost a 1. I'm going to say 0.95. It's a 0.98. Yeah. So I just had a bunch of really easy ones for me, honestly. Maybe because I've been playing Guess the Correlation game long enough, I'm finally getting better at it. But I would check it out and see if you can get a hang of what a correlation looks like, because I think we look at the number, we don't know what it means, but we look at the data and we're like, oh yeah, okay, it needs to be really tightly clustered along that line to be a strong correlation coefficient. So enough on that. Come on, little mouse. There you go. Come on. There we go. All right. So we got to be really careful now about confusing correlation for causation. The reason we're interested in correlation is because it might indicate there's a relationship between two variables. But there's a lot of things that are correlated that don't have a causal relationship. The example that Whelan gives is a great one, which is that the number of TVs in your house is correlated with the SAT scores of the students living in that house. Now, does watching more TV or having more TV available to watch help you do better on the SATs? And it would seem like if correlation meant causation, that would be what's going on. But what Whelan does a great job of explaining is that no, it's not about that at all. In fact, it is that high school students from rich families have both more advantages in taking the SAT, things like test prep, things like their parents encouraging them to do college prep classes and be concerned for the SATs, and they also have more TVs in their house because they're wealthy. So the real cause is being from a wealthy family that's causing both TVs and higher SAT scores. And we know that lower income families have a more difficult time with both scoring high on the SATs and owning more TVs. So that's not a bad example at all. And then I want to get into this stuff really quick here, which is this whole list. And I'm going to go back to my Google Keep and diagram each of these in turn. I'm going to pull them all out like this, and then I'll explain them in turn. Actually, I'll explain each one. A causes B. It could be A causes B if A and B are correlated. So if we have a correlation between A and B, it could be that A is causing B, and that makes sense. That would be good. What I like to do with this is I like to draw a causal diagram, and this is not like a fully formal in psychology causal diagram, but where's my mouse? Hold on a second. I gotta figure out how to get a new screen. There it is. All right. So let me just pull this one out of here, and then I can draw it over here, and it'll all be okay. So here's what I like to think about annotating this sort of thing, which is I can show you what, man, the struggle is real. I can draw a box around a variable and give it a name. How did I choose orange? I am just going to post this. I'm not editing anything. I'm not skilled enough to edit stuff anyways. And then, what is going on with the orange? That's what I want. There we go. Okay. And I'm going to make it a little bit skinnier on the tip of the pen there. Just for, there we go. That'll be fun. All right. So the way I like to annotate this, just so we can, did I just do that? There we go. The way I like to annotate this, just so we can get a visualization of it, is we think about thing A as a variable, and we draw a box around it because it's something like number of TVs, and then we can draw a line, and we can put a box around something that we can label B, like SAT scores. And this is saying that A causes B in a very messy way. And so this is what we call causation. Okay. But we can also have, I called it causality on my other slide, but same idea. But we could also have B causes A, which is reverse causation. Boy, I'm sorry, that is really pretty awful. I wish there was a way for me to type and note on this easily, and I don't know that there is, and I don't know that it's going to get any better. What I should be doing is having the camera with a whiteboard behind me, but I don't have that tech going, so I could just go to a school someplace, I guess. Let me bring the other one back, because you can see the diagram now, but it's messy enough. I'd rather have you just be able to read it easily. So we can have A causing B, which is causality, what we very often assume to be the case. But there's lots of examples, and don't worry, my next presentation, we're going to go over some of these examples of reverse causality, where we see actually people think it's A causing B, but really it's B causing A, and it's a problem. You can have bidirectional causality, which is that A is causing B, but B is also causing A. So if A is causing B and B is causing A, then you have a hard time picking out which one is actually causing which, right? It's a chicken and egg kind of problem if they're feeding off each other. We're going to come to some examples of that as well in our next reading from Huff as well. A and B could be caused by X, which we call common causality. So I'm not going to write my terrible script up here, but what I will do is I'll write just a notation for it here. So bidirectional causality is A causes B and B causes A. I'll give you the example from Huff that's really good, which is A is being rich and B is investing in the stock market. So if you look at people who are rich, almost everybody invests in the stock market who's rich. But if you look at people who invest in the stock market, hardly anybody who's poor invests in the stock market. Why? Because you need to have money to invest in the stock market. Sure, right? But arguably, investing in the stock market is one of the ways that rich people get even more money. So A causes B, being rich causes people to invest in the stock market, but so does investing in the stock market cause people to be rich. And untangling those two things is really hard because it's hard to find somebody who's rich that doesn't invest in stocks. And it's also hard to find somebody who invests in stocks that isn't rich. So not a bad example of bidirectional causality. That's from the Huff reading we're going to do in a minute. And I didn't want to leave you hanging too long. The relationship that we said here incorrectly, which was having TVs causes high SAT scores, is much better explained by this relationship, which is that some factor, X in this case, some third factor, causes both A and B. Oof, boy. Come on, Tim, you can do it. Almost done. There's A and there's B. So X causes A and B. This is a much better explanation for the case of a rich parents cause both lots of TVs in the house and kids who do a little better overall on the SAT, right? And because it's rich parents causing both those things, households that have lots of TVs are also households that have kids doing better on the SATs, but we don't actually have a relationship between TVs and SAT scores. It's the rich parents that are causing both of those things. That's what we call a common causality case. We just looked at that. Oh, let me get back to my mouse and my trackpad are fighting with each other. There we go. Okay. So both A and B caused by X, common causality. You can have A causing X and then X causing B, which is an indirect causality. And that seems kind of obvious, but it's important to think about because you can have A and B observed, and then X is something that's unobserved that is necessary for A to affect B. But if you don't pay close attention, you might miss that. There's lots of examples of this missing factor or this missing clue in a whole bunch of domains. But one that springs to mind is that a lot of marketers see something a marketer's doing and they copy it, but they don't quite get the formula right. They're missing a little something and they end up not creating market demand. They end up flopping, right? So this idea that A is indirect causation. There's something causing something causing something, and so you need both of the things to cause the final to push them the variable. If A is causing X and X is causing B, then A and B will be correlated, right? But A by itself is not causing B. It's only causing B through X. That's what we call a mediating variable in psychology, but it's worth thinking about. Last, and most importantly for our discussion of causation, we could see a relationship between A and B in terms of the statistical relationship between A and B. A and B could be strongly correlated even, and it could be completely accidental. which is why we say correlation does not equal causation, because we want to be hyper aware about the idea that just because there's a correlation doesn't mean that there's any of these other things going on. It could just be an accidental or spurious correlation. That's the end of that slide deck. To finish that up, I want to take you back to the week 4 module and show you this bonus material little presentation here, which is Tyler Vegan's spurious correlations. We'll open that up. And what this is it's a collection of correlations that are all pretty darn strong correlations. Some positive, some negative, but pretty strong correlations. But this fellow Tyler Vegan came up with these correlations by just randomly trying variables against each other again and again and again until he found a correlation. And that's something you can do. You can take a massive set of data and another massive set of data and correlate all the variables with each other. And sooner or later, one set of variables will be moving along with the other set of variables and you'll have a correlation. And then you can say, look, I found a correlation. So what Tyler Vegan does here is he presents some of the most outlandish ones, like, for example, there's a strong positive correlation between U.S. spending on science, space, and technology and suicides by hanging, strangling, and suffocation. Now, which is causing which, first of all? Is it the increased specific kind of suicide that's causing the U.S. to spend more on science, space, and technology? Or is it spending on technology that's causing more suicides? Or is it a spurious correlation? One thing to note here, and we're going to get into this in the Huff reading, is first of all, there's a very short data series. It's only a 10-year series, I guess 11 data points overall. So that's one way to get a spurious correlation, is to have relatively few data points. Second of all, it's two things that are increasing over time, and you can find a ton of things that are increasing over time, right? So you have to be careful with that. Number of people who drowned by falling into a pool, strongly correlated. And so this one, the correlation, by the way, it's given right here. It's 99.7%, or R value of 0.997. Like, just insanely high, right? Almost 1. The number of films Nick Cage has appeared in is strongly correlated, R of 0.666. With number of people drowning by falling into a pool. Per capita cheese consumption correlates 0.94 with the number of people who died by becoming tangled in their bed sheets. So cheese consumption is going up, and so are deaths by bed sheets. Right? Like divorce rate in Maine and the per capita consumption of margarine. So some of these, I'm sure you just rolled your eyes and said, wow, that's silly, right? But some of them, I bet some of you, maybe just me, maybe I'm the only one, but some of you probably looked at them and said, well, maybe I'm, and you tried to think up a story about why that might be. This is the problem. This is the siren song of the spurious correlation. We have to be very careful about this, because we can get sucked into, when we see a correlation, creating a story that explains the correlation, and we don't want to do that. We want to start with what we think the story is, and then looking to see if the evidence supports our story, not finding a random correlation and then making up a story that explains why it's the case. The more we do that, the more we fool ourselves. And it's a very human tendency to try and look for patterns, right? We see a man on the moon, for example. We want to have a convincing explanation about why something that is really totally random actually totally makes sense. Let me explain it to you, right? People who think in conspiracies, by the way, just have that dial turned all the way up to 11. They see something that is a spurious correlation, and it all just makes perfect sense, to the point where they have the blinders on, where they disregard information that's disconfirming and only pay attention to the confirming information. And so then they end up with this sort of like, well, you see, it's because in Maine they eat more butter, and right, they come up with some kind of story. that is a good spot to end it. Be careful of the spurious correlation, and I hope I hope that wasn't too painful for y'all. It felt painful for me because I'm just struggling along here with the whiteboard, but I'm actually I'm not too defensively proud of my my scribbles. And if you want to send me some feedback about whether those scribbles were useful or not, I'm happy to listen to your kindly couched criticism and see if I can do something better when we go on here. That's all for now. I'll talk to y'all soon, and have a great few days before I post another one of these.